Hi, in this video we are going to look at an exam question, a CT4 exam question which appeared in September 2013. This is question number 3 in that paper. The ideas involved in this question are found in the readings for the new CS2 syllabus under the Stochastic Processes chapter. So let's read the question. In part 1, you're asked to define a Poisson process. This is classic textbook work. A bus route in a large town has one bus scheduled every 15 minutes. Traffic conditions in the town are such that the arrival times of buses at a particular bus stop may be assumed to follow a Poisson process. Okay, the important things here. A bus route in a large town has one bus scheduled every 15 minutes. Keep that in mind, yeah? Mr. Bean arrives at the bus stop at 12 midday, yeah? 12 noon. To find no bus at the stop, he intends to get on the first bus to arrive. In part 2, you are asked to calculate the probability, or rather determine the probability that the first bus will not have arrived by 1 p.m. the same day. Basically, no buses arrive in the first hour. Good. And then they go on. The first bus arrived at 1:10 p.m. but was full, so Mr. Bean was unable to board it. Part 3 says, explain how much longer Mr. Bean can wait. Again, how much longer Mr. Bean can expect to wait for the second bus to arrive. Pretty easy. This is from the memoryless property. I'll talk about it in a minute. Part 4, calculate the probability that at least 2 more buses will arrive between 1:10 p.m. and 1:20 p.m. Again, calculate the probability that at least 2 more buses will arrive between 1:10 p.m. and 1:20 p.m. So we'll move between the solution that I provided and the question to and fro. Now the first part, the Poisson process, where we asked to define it, that's book work, so you can look it up. So this is directly taken from the core reading. A Poisson process with rate lambda is a continuous time, integer valued process, n sub t, I'm just going to call this nt, nt, t bigger than or equal to 0, with the following properties. N0 is 0, nt has independent increments, okay, nt has independent increments, and nt has Poisson distributed stationary increments. Don't forget to write down the formula. Probability nt minus ns equals to n equals to this formula that you see here. Okay, s less than t and n equals to 0, 1, and so on. Now, you can easily remember this formula by thinking of e to the power minus lambda, lambda to the power of x over x factorial. That's the basic Poisson formula we learned some time ago, yeah, in a statistics class. Okay, except that now here we are dealing with increments, t minus s. Again, look this up, very important. Nothing much I can say about this part, yeah, except that it's plain textbook work. Now, let me come back to the problem. We have a town in which we have one bus scheduled every 15 minutes. Yeah? A bus route in a large town has one bus scheduled every 15 minutes. So this guy arrives at the bus stop at 12 noon, and we asked to determine the probability that the first bus will not have arrived by 1 p.m. the same day. So no buses arrived in the first hour. So from the bus schedule, we have one every 15 minutes. Therefore, we have a rate of 4 per hour. So my mean rate is 4 per hour. Lambda is 4 per hour. Now I've used x here. Don't worry about it. If you would like to use nt, that's fine. But I'm using x here. We asked to find the probability that no buses arrive in the first hour. You can think of it like this. X is Poisson with parameter 4 per hour. So we asked to find the probability that x equals to 0. What is x here? X is the random variable defining, or rather is representing, the number of buses that arrive in an hour. Okay? So probability x equals 0, plug into the formula. We have e to the power minus lambda. So e to the power minus 4. And lambda to the power x will be 4 to the power 0. X factorial will be 0 factorial, which is 1. So your final answer turns out to be e to the power minus 4. Use a calculator and you'll get 0.0183.